Hey everyone, and welcome back to Data Structures and Algorithms. If you ever worked with data, you're probably familiar with lists and arrays. Data structures that store items one after another in a straight line. But what happens if your data isn't linear? What if it's hierarchical, like a file system on the computer, a family tree, or even the structure of a company? That's where trees come in. Unlike list trees, are data structure designed specifically to manage hierarchical data, giving us a powerful way to represent relationships between items. So what exactly is a tree? At its simplest, a tree is just a collection of nodes which hold our data. For example, the data can be numbers, and the nodes are connected by edges. You can think of it like a family tree where each person is like a node, and the lines showing parent-child relations are the edges. To talk about trees, we need some specific vocabulary. First, every tree has a root. This is the single node at the very top where everything starts. From the root we have relationships. A node that has branches leading to other nodes is called a parent node, and the nodes it connects to are its child nodes. If a node has no children at all, we call it a leaf, and any node that isn't a leaf, so it has at least one child, is called an inner node. And finally, a sequence of connected nodes from one point to another is called a path. So if we want to go from the root to this node, we have to go this path. We can also measure trees. The level of a node is how many steps it is from the root. So the root itself is at level 0, then its children are at level 1, and their children are at level 2, and so on. The total height of the tree is just the largest level number plus 1, so in this case the height would be 3 plus 1, which is 4. Additionally, a tree with a maximum of n children is called an n-ary tree, so the tree on the left has a maximum of 2 children per node, and that's why it's called binary tree, and the tree on the right has a maximum of 3 children, so it's called a ternary tree. So the tree from before is also a binary tree, because it also has a maximum of 2 children per node. Also, we call a tree ordered if the nodes are arranged in any sorted order. So in a binary tree, each node can have at most 2 children. We have a left child and a right child. This simple constraint makes them incredibly powerful and efficient. Within binary trees, you sometimes hear the terms full and complete. A full binary tree is one where every node has either 0 or 2 children, and a complete binary tree is even stricter. It's a full tree where all the leaves are on the same level. Okay, so we have this great structure, but how do we actually visit every single node to read or process its data? This process is called traversal. There are two main strategies. Depth first search, or DFS, where we go as deep as possible down one branch before backing up. For DFS we have the traversals in order, pre-order, and post-order. And breadth first search, or BFS, where we explore the tree one level at a time. For BFS we have the traversal level order. We will explore DFS and BFS closer at a later point. So let's look at the 3 popular DFS methods. The rule is first left, then root, and then right. We will traverse the left subtree, so we go all the way down the left side, then visit the root node, and then go down the right side. For this expression tree, an in-order traversal gives us the standard infix notation we're all familiar with from math class. So we start from the root and go all the way down on the left side until there is no left child anymore. So then we can print our first node, which is 2. Then we visit the root, which is the asterisk, and print it. And then we visit the right node, which is 5. Now we visited the whole left subtree. So we can visit our root node, which is plus, and go to the right subtree. And again go all the way down on the left side. So the next node we print is 2. Then it's root node plus. Then the right child 1. Then the root of this left subtree, which is an asterisk. And then its right child 3. So this would be our output for the in-order traversal. Next order is pre-order traversal. This time the rule is root left right. We visit the node first, then traverse its left and right subtrees. This generates what's called prefix notation, where the operator comes before the numbers. So we start from the root plus and print it. Then we go to the left subtree and print the asterisk. And then its left child 2 and its right child 5. Then we visit the right subtree, which gives us asterisk, plus, 2, 1, and 3. So this would be the output of our pre-order traversal. And the last one is post-order traversal. You can probably guess the rule, left, right, root. We traverse both children subtrees completely before finally visiting the root node itself. This produces postfix or reverse Polish notation, which is famous for being used in some old calculators. First we visit the left subtree, so we have 2, and then we visit the right subtree, so we have 5, then we visit the root node asterisk. Next we visit the right subtree, so first we have 2, then 1, and then plus, then 3 asterisks, and finally at the end our root plus. So these would be the final expressions for every traversal. Important to know is that the in-order traversal is not clearly. We would need additional parentheses. The other major strategy is level order traversal, which is BFS. It's more straightforward. You simply visit the nodes level by level from left to right. So first we visit the root, then all its children, and then all their children, and so on. This method is usually implemented with a queue. We start by level 0, enqueue the root, which is plus, and visit it. Then we dequeue it and enqueue the two children nodes and visit them in order. So we dequeue the first asterisk and add its children 2 and 5. And because we have a queue, it ensures we maintain the correct order. Now we can dequeue the second asterisk and enqueue its children plus and 3. And the next step is to dequeue 2. Because it has no children, we can also dequeue 5. These are the leaves for this subtree. So we're done with the left subtree. We continue the same with dequeuing plus and enqueuing its children 2 and 1. And finally we can dequeue 3, 2 and 1. So this would be our final output for the level order. Traversal is great, but the real power from trees comes from being able to find information very quickly. This is where the binary search tree or BST shines. And BST is a binary tree with one important rule. For any node, all values in its left subtree are smaller than its own value, and all values in its right subtrees are larger than it. So here you can see all nodes on the left of 8 are smaller, and all nodes on the right are larger. This simple rule makes searching incredibly fast. To find a value, you start at the root. If your value is smaller than the node's value, you go left, and if it's larger, you go right. And we keep doing this until we either find the value or we run out of nodes. It's like a guessing game that cuts the remaining option in half with every step. For example, if you're looking for the node with the value 5, we start by root 8, 5 is smaller than 8, so we go left. Then we have 4, 5 is larger, so we go right. And then 5 is smaller than 6, so we go left and reach our node. The time complexity of searching in a binary tree is bigger of log n on average, with n being the number of nodes. So let's recap. Trees are a fundamental hierarchical data structure. We learned the basic anatomy, the different ways to traverse them like inner order, pre-order, post-order and level order, and how the special ordering of a binary search tree allows for incredibly efficient searching. From file systems and databases to 3D graphics, trees are absolutely everywhere in computer science. So that's it for today, thanks for watching. If this video helped you understand trees a little bit more, give it a like and subscribe for more content on DSA. If you have any questions, drop them in the comments below, and see you in the next one.